40 miles per hour. And we want to test a model which is 10 times smaller in the wind tunnel, whereby I want to maintain the same speed. That is condition given. Part A, same temperature in the wind tunnel, which is ambient. What air pressure is needed in the tunnel? I mean, it seems the problem is very vague. I mean, it's like not a lot of setup in the conventional way you have seen for dimensional analysis, but it actually all boils down to the same old, same old. So you saw an airplane, if it helps for you to see, just assume it's an airfoil. So for the first part, where you're doing model analysis, similitude is what we are after. That's what we are asking you, right? So from your wisdom of dimensional analysis, what pi term will be of first significant to this problem? The part B, I should also state, asks for the drag on the prototype if the model force measured in the wind tunnel is 1 pound. 1 pound. So first and foremost, from dimensional analysis, what can you tell me for a problem by an airfoil? What are the pi terms that will dictate the physics of this problem? Reynolds number. Reynolds number. That's all. That's all we've been drilling all the time. It's the Reynolds number, nothing but just the Reynolds number. And that's part A. So let's walk through that. Or instead of me walking through that, I will just tell you the answer is 10 times. What pressure? 10 times. Your job is to redo the problem and tell me why 10 times. All right? Yes?
How do we know for this problem, like, where to, like, substitute in the ratio and 10? Like,
Okay.
for A or for B?
Okay, so that's your homework. And the key is to match what number between the model and the prototype? What dimensionless perimeter you want to match in order to have similitude? The Reynolds number. So the key to what you just asked me is you have to match the Reynolds number with the prototype. And with that, no change in temperature, you will have to use ideal gas. That's maybe the missing link, but it's meant to be a pretty simple problem. Right? You don't let me change the velocity, and you don't let me change the temperature, and you string the model by 10 times from ideal gas, I have to jack up the pressure in my tunnel by 10 times to match the Reynolds number, no more, no less. This is how you do this part A. Do you understand what I'm saying? And if you ever go to NASA Langley, there's a historical landmark, certified by ASME of this high pressure tunnel, 10 atmosphere, was built way back, maybe in the 30s. It's not very big. It's about probably from half the size of this room, about the height of this room, but a high pressure vessel that indeed can create a 10 atmosphere difference. And they test airfoil in that very elementary tunnel before. Yes?
Is the density constant for the prototype of the model? Is it the
Say
same?
that again.
Is the density the same for the
No.
It's not.
Think about it, ideal gas. Think about it, ideal gas, right? Temperature the same. Pressure 10 times. What is it doing to the density? And And that change is what matches the Reynolds number.
So could you also use the pressure coefficient to do this problem?
Say that again?
Could you also use the pressure coefficient to?
There's no pressure coefficient that I'm interested in, because all I care, what is pi 1? What's pi 1? The drag coefficient, right? So again, it's not a traditional dimensional analysis problem that you have seen in chapter 8, maybe that's what throw you off. But I'm not asking for a pressure coefficient, but for part B, I'm asking for drag coefficient, which is the drag force. How do you formulate pi 1? This you have seen many times. You have to go through that, raising the exponent A, B, C, you will have no time. So how do you do the pi 1 term? How do you formulate the drag coefficient? What does it look like? What combination in the denominator will give me a force? Huh? Pressure times an area? Okay, fine. Can you further change it to something related to my problem? 1/2 rho v squared. Yeah, what pressure? I don't want you to start another pressure coefficient, that's not what I'm after. It's 1/2 rho v squared, right? Times what? Times what? What's the area? Name square. That's the drag coefficient. That's a pi 1, right? And that by matching, so we'll call this drag coefficient, prototype, model, you will be able to get the actual force. So it's meant to be a simple problem, but a lot of you struggle with it. Perhaps just because the way it's set up is not like what you see in the homework. So please rework it, it will take you 5 minutes. Now you understand how to attack the problem. Yes?
So you're saying that they have the same drag coefficient?
Well, what do you think?
Yeah.
You're not sure, let's let me back off one step. Do you think the Reynolds number should match?
Yeah.
Yes, it's called similitude. Right? If I match the Reynolds number, in this problem, it's very simple. There are only 2 pi terms. My Reynolds number, if they are matched, that means my pi 1 term, which is the drag coefficient, must also match between the prototype and the model. And that's it, and that's all you're asked to do. And by matching that and knowing the other parameters, you can get the prototype drag force. So they're a little detailed, but you can work it out once you have this background. Okay? So, the pipe flow problem is not difficult either, and it's set up step by step to let you to the final answer, and so it's relatively easy. Analysis, in that you are guided by the problem statement, a step at a time, to analyze this problem. So let me give you all the peculiar. So I have a machinery in the flow path of the plumbing, which I don't even know whether it's a pump or compressor or rather, sorry, pump or turbine, but you were asked to determine whether it's a negative work, meaning it's a pump, or positive work, meaning it's a turbine. So this height here and all this detail need to be drawn accurately. You have a reservoir where you are told the pressure is atmospheric at the elevation of 12 meters. You are even told the reservoir velocity, because of the large area, is relatively small. You have in the plumbing a valve a turbo machine that is not long as the pump or compressor. You have at the exit a large reservoir to collect the residual. So the pipe exit is just slightly lower than the fluid reservoir. So instead of 12 meters, the difference is only half a meter in height. And the fluid in this reservoir contains of two different types, and there's a reason why there are two different types. Because the density is not the same, and you have to be very careful how you apply the energy equation. So we have oil and water. The pipe diameter is huge. It's 1 meter, so it's a gigantic pipe, not your typical small pipe. What added, and because of that, you can have multiple answers due to how you approach the problem. The reservoir surface where velocity is negligible is 10 meters. So let me give you all the constancies that you need to do the problem. Flow rate, 50 kilograms per second. All the minor losses are tabulated. So you will need this to complete your assignment. And you are told it's a smooth pipe, so you know where you are on the roughness of the pipe. And density of water and density of oil are both given. I think that's all there is for the problem statement, and you have now everything you needed to rework the problem. I think, yeah. Yeah, all the elevation is given. 12 meters at the very top of the tank, 5 meters is the length of the oil, and then 11.5 meters for the exit of pipe 2, and 10 meters the surface of this reservoir that received the fluid. So, let me give you all the parts that were asked. Part A, velocity in the pipe, meter per second. Because of diameter, I'll just give you the answer. And I think most of you will know to use continuity to get to this answer. And it turns out the velocity in the pipe of 1 meter is very, very small. 0.06 meters per second. And because of that particularity or that geometry, when you apply the energy equation, the velocity term actually is quite negligible. All right, so part B is set up specifically so you hopefully it's a hinge to do the last part when you apply energy equation. So tell me the pressure at the interface between the oil and water. How do you get that? Tell me the pressure here, which I will call 0.1. OGH. There's no trick to that. It's just OGH, which again I'll let you do the calculation on your own. OGH will give you that column of oil on top of the water is equivalent to about 44.6 kilopascal. And I'm jumping ahead, I'm having that part B set up so that I hope with that hint, you will use energy equation at 0.1, but not at the surface of the oil. Because if you use the surface of the oil, you have different density fluid. Part C, Reynolds number, that's piece of cake. That's just something you have to make sure you calculate correctly. And part D, friction factor, then the smoothie diagram given on the back of the page for smooth pipe, you get that to be on O2, so again, you can check all of this. So nothing hard so far. Friction factor, which I hope you have no problem calculating. The velocity being so small, the friction factor that's calculated turned out to be relatively small also, like on 1 meter. So it's not your typical pipe problem because of the 1 meter diameter of the plumbing, right? So giving you all the answers, what is all the minor losses, which again they're broken up into pieces for ease of getting to the final answer. So the problem actually is broken up piecewise to help you to get to the end. Again, because of the diameter being so big, velocity is so small, all the head loss due to minor component is again very small, 2 centimeters, not very typical of your pipe flow problem. But so far, any question? Very mechanical. This is nothing that you shouldn't be able to do. Now the last part is where there can be some ambiguity, but either way you do it, you get credit. So let me give you the way that one solution to the problem is starting from point 1 as shown on my diagram. Where all the other minor friction losses are incorporated. I have a subscript here wrong, sorry. V2, please pay attention. For my solution was chosen at the exit of the pipe. If you do that, there's a finite velocity at 2, which as I mentioned, turned out to be very insignificant, very small. But despite that, if you plug in all the value in here, you will get the answer, and coupled with the power of the pump, to be calculated by this equation. So I get the HS from the energy equation, and then subsequently I use the power law to get the full work, and my power based on this analysis is negative. That's the pump. It's a little less than 1 kilowatt. All right? Any question on that? I left out the detail for you to fill in. The alternative solution, this is one way that's acceptable. Yes, the problem is laid out there another path of which you can get to the answer. I'll call it 2 pi. You still have to start with 1. You cannot start with the surface of the oil because they're different density. So start with 1. If you take your endpoint at 2 pi, you rework the problem, turns out you get a different answer. So if you use 2 pi, you get an answer of about 244 watts. All right, so both are acceptable because of the way the problem is set up, and you get full credit depending on what you pick. So I thought this test is a little intricate, but it will serve a good purpose to prepare you for the final. Yes?
So why did you choose from like points 1 and 2 as opposed to like 2 different points?
Say that again, why did I choose point 1 here?
In your Bernoulli's equation,
It's not Bernoulli, no, I'm applying energy equation.
right, energy equation, my fault.
Right.
In energy equation, why do we choose from 1 to 2 as opposed to 2 different points?
Such as what? Give me an example.
2 to 3,
Where is 3? 2, where is your 2?
where you have your 2, and I guess I should have
2, okay, 3 is here.
No. Never mind.
There are not many choices.
Yeah.
There are not many choices. Yeah, it turns out, by design, I don't want to choose this as point 1 for the reason I mentioned. And I purposely set the problem to get you to here. The only ambiguity was the given height here that led to two different answers, but that's, both approach would be acceptable. All right? Okay, so I want 5 minutes. Okay, I think maybe I should stop. Give you time to work on the quiz. Yeah, I'll start the new topic next time.
Gotta get to, let's see, nothing's gonna work.